Okay, so the purpose of this video is to give you a general idea of what a linked list is and basically how it's structured. So to do that, we have to do a little bit of a review on what a reference data type is. When you think about a reference data type, everything in C# or in most all managed frameworks is basically a reference data type. So every button, every object, even, well, primitive data types aren't really referenced, but essentially everything, every piece of memory that you ask for is a reference data type. And what that means is the reference itself in old languages would refer to that as pointers. And when you reference and use a reference object or data type, what you're doing is you're going to create a variable that's going to hold the address of the actual data in RAM. And so it's a physical thing, and I want to go ahead and demonstrate the idea of a reference data type as it is with or for an array. So let's call this linked list, and we're going to be adding to this as we progress. We're going to start with poor man's linked list, and then I'll go into a video about the linked list manager, and then of course we will continue on with the completion of the linked list, and there'll be a portion where you'll have to finish on your own as part of your assignment. And then we'll probably do a video that'll put some bells and whistles on it, such as make it into a doubly linked circular list. So let's start with just what a reference data type is. Whenever you declare an array, basically the name that you give the array is the reference type, and it's a pointer, and all pointers are 4 bytes. And essentially there's two components to a reference data type. The first component is its address, where it's located, and that you can view by looking at in this diagram that I've got. I've kind of put in an address here, 2014. That's arbitrary. Basically, I made that up because the compiler deals with that for you, or not the compiler, but the IDE. So when you declare a variable, you're declaring a reference type that has an address that's given to you automatically, and is going to store the address of another piece of data. And that is what you're going to assign. So when we create an array, and what I'm going to do here is I'm actually going to go in and I'm going to do everything in form 1 load. The array that we're going to create is just a simple integer array, and I'm going to call it iArray. So the iArray pointer we've just created. That's all you need for a reference data type, is to declare an array and give it a name. And reference data types don't have to be an array. They can be a button. That's a reference data type. Now, it's when you go to instantiate the button or the array where you actually are assigning the address of what the reference type points to, the data or the address point of where it's going to be stored in RAM. So reference data types have their own address that is automatically assigned, and they're going to hold the address of memory or the location of memory for its data type. So in the case of iArray, when we instantiate it, whenever you ask for that memory, you're going to use the new operator. And I'm going to probably zoom in on this a little bit for you, probably a little better. So we're going to say I want a new integer, and I want 3 of them. Okay, so essentially what I've done with this new is I said assign, give me an address, because before, without that new, what you want to do is you want to assign it null if it's not pointing anywhere. So that means that the value in here of where the reference type points to will be 0 or null for iArray. So essentially, basically what we're saying is it points nowhere. Now I'm going to actually assign it some value, and I'm going to ask for a new set of integers, 3 of them. And what happens is I'm going to receive from the operating system, basically I'm saying, hey operating system, give me 3 integers and give me the starting address of those 3 integers. And the starting address is what's going to be held in the reference type. And essentially what ends up happening is you ask for them. Oh, it looks like I got 4. You ask for those 4 integers, and your return is the starting address of each integer. So every integer that you have, or every variable that you create, you're essentially, there's a physical location in RAM where that variable resides. And if I'm asking for 4 integers, the operating system is going to give me the starting address of that 4 integers, and that's what my reference type is going to hold. So this reference type, iArray, is my doorway into those 4 integers. And the way I use them is by saying iArray of 0 equals 1. So what happens is I'm saying go to iArray, and what it points to, its 0th element, and assign it 1. Then I can do iArray of the first index equals 2. What I'm saying is go to iArray and go to the second element and assign it to 2. Now, here's the thing with arrays. What we refer to them as is contiguous memory. Contiguous memory means memory that's in order. And that's why the reference type that holds the starting address only needs the starting address, because everything else after that is contiguous in order, meaning an integer is 4 bytes. So the first integer is going to have a starting address, and then the second integer is going to be 4 bytes more in order and contiguous. So I get back from the operating system, I ask for 4 integers, I ask for 20 bytes, and it's going to give me the starting address of those 20 bytes. And that's the very beginning of that array. So the 20 bytes are from address 100 to 116. Well, it's 16 bytes. So yeah, 4 times 4, 16. So it's not 20 bytes, 16. So you only need the starting address. And once you have that, the rest come along. There's a problem with this, though, is because contiguous memory, since you ask for this memory all in one chunk, you can't just say, oh, okay, well, maybe I want another one. Give me one more for 5, starting at 116. And the reason being is because you don't know if that address is being used by another program. So when you first ask for those 4 integers, the operating system finds 16 free bytes for you. And they are going to be 16 bytes in one block that's all in order, contiguous. If you ask for any more, you can't just go along after you've declared it and say, hey, give me an extra one, because you have no idea if another program is using that extra bit or that extra address space in RAM. And that's why contiguous or arrays themselves are a problem, because they have to be created for a specific size, and you can't just add more. You have to create a whole nother array. If I wanted to increase the size of this array, I would have to create a whole nother one and basically make it 5, give it another name, and then copy the contents of the first array into the second array, which is wholly inefficient. What's nice about static arrays is they're very fast. If you want to get to the fourth element, it's fairly, it's really quick. And that's why it's good to use for, maybe if you're accessing hardware and that memory needs to be filled up, based on a time span of milliseconds or something like that. So arrays themselves, contiguous arrays, good because they're fast, bad because they're not dynamic. You can't grow them on demand. So that's why we have linked lists. Linked lists are a little bit different. And the way a linked list works is instead of being contiguous, everything points, or each data point, such as each variable or data point in the array itself, will hold the address to the next value. So I've got a good diagram here to kind of contrast. So here's kind of how a linked list works compared to a contiguous array. This is an example of a linked list. It has a reference. It's a reference type that you use. Basically, its name, just like we have array and we use new here, or even just like we have a button and we have to instantiate a button with equals new button here. Basically, we have a reference type, the name of the variable itself, and that reference type is going to hold the address of the first, and we call these nodes now. And what each node has is the ability to store information and also to point and use another reference type inside of it called next that points to the next node with its information, and of course another next that points to the next node with its information, until finally the next reference inside of that node points to null or nothing, and you're down to the end of your data. So basically the difference here is contiguous array, every next item is managed based on contiguous memory that's in order, versus a linked list, every data item or data point holds the location of the next one. And things are a little bit different when you're working with linked lists, and we call that dynamic memory. So I'm going to kind of give you an idea of how dynamic memory is done with what I call the poor man's linked list. And this will be kind of your intro into what a linked list is. I'm going to pause it for a second and then I'll be right back. Okay, let's go ahead and take this from the top. What I'm going to do is I'm going to build a linked list, a poor man's linked list, and I'm going to diagram it, kind of use this diagram as we go. I'm going to go ahead and get rid of this guy. Don't think we need him anymore, but we can bring him in here in case we need him. We'll use this guy right here, this diagram, to kind of, show things as they're happening as we progress and work through and create a linked list. And we'll start with just the reference type and then add nodes as we go. But that's essentially what we are doing, is we need to create our own data type, our own object. It's called a node, and that's what represents each of these guys. This is a node, and what a node does is it contains a variable for some kind of storage, and it contains a reference type for the next item in the list. And the way that takes form is first by declaring the node itself. In fact, that's all you need for a linked list is a node object. So what we'll do here is I'm going to go ahead and go in here to project, and we're going to add a class. And go ahead and call this node. Okay, so the class itself we're going to make public. However, we're going to make everything else that's inside of it private with an accessor, so we'll refactor. So the two attributes of a class are some kind of storage mechanism to store something and a next variable. So it's kind of interesting how this works out, but essentially we don't want to have an integer called storage or a string that we store, because essentially an integer, string, even buttons, everything in C# has a low-level class that everything inherits from, and that means that everything that you can create in C# down to primitive variables, integers, doubles, floats, buttons, text boxes, whatever, they all are objects. So if we declare an object as our storage, we can store any kind of variable we want inside of our linked list. And that's called boxing and unboxing, and your book talks about that. So I'm going to go ahead and put a little comment here using an object. And so we're going to box all types of variables. So basically, since we have an object for our storage, we can use every node to store an integer, string, button, text box, form. We can even have a linked list of forms if we want. So that is fairly simplistic. In fact, we can, if we want to, we can have two storage. So every node can store two items, but that's kind of redundant, so we don't really need to go into that. Now here is where you go with the next. So we have the storage. That's this attribute right here, what we're actually storing in the linked list. And now we need this reference type that's called next. The reference type is just like any reference type. So any reference type that you have, you're going to first declare it and then instantiate it. So what we'll do is we're going to start this out so that every node is essentially begins with a next that points nowhere. So essentially this will be null. And it will not be linked. And we haven't even really created one yet, but this is just kind of what it's going to look like right as soon as we get started on it. So what you do is you create another node, or you define a node that's going to exist, and you're going to call it next. And what it's going to do is it's going to store, and it's a reference type, so it stores an address just like any reference type. And this is going to be the start of our list. So that every node itself is going to store the next location of the next node on the list using this next variable that's also a node. So you can kind of think of, if every node has a next, and you create every node, and each one has a next, then you create one and it has next, and then that one's created and it has next. Basically, you've got to control the instantiation of every node's next, because every node has a next. Kind of a little bit of a twister there. Basically, I kind of consider it as digging a hole in the ground. But basically, the node next, as long as you control it with setting it to null, as soon as it's instantiated, that means that it's not going to create another node, because literally it's just a reference type. So it's not a node until you say equals new node. It's a reference type, not a node yet. And that's why you need a constructor for node. So the constructor for node, what it's going to do is it's going to essentially say next equals null. And that's where the next reference type has its own address that's automatically assigned, but what it's going to store is nothing. it doesn't point to another node, because whenever we create a node, we don't want it to create another node. We want to control that creation. Basically we do it with the linked list manager, which will be part of my second video. I'll be showing how to do that. Right now I'm going to show you how to do a linked list without a manager. So this is essentially all you need for a linked list, just this little bit of code, and we can start creating a linked list. We don't have this yet. We haven't created a node yet. We've just defined what a node is going to look like. You may want to do something like setting storage equal to null also. But what we're going to do is we're going to actually be assigning to storage some primitive data types, so such as an integer or double or float. So we won't have to do much. We won't actually have to use the new keyword for primitive data types. But that's going to come in the form. So this is everything we need for our node. Let's go ahead and start working with our node. And basically, the start of this all begins with a reference data type. And that is always referred to as the head. The start of a linked list is the head. So when we create a head node, we're going to say node head. Okay, so far in our code, this node head, this is what we have. Basically we have a reference type, and I'm going to take that reference and I'm going to assign it to null, and it has an address of where it's located in RAM, but it's going to point nowhere. That reference type does not point anywhere, and it's not going to point anywhere until we do this. So we say head equals new node. That's when we say, hey, operating system, give me the first byte of that block that's needed for a new node. Now it looks like I've got an error here because I didn't make my I did not do some things with the node that I should have done. Looks like we've got to make the constructor public, and we've got to refactor these. Let's be explicit in their access, make them private, refactor them. A few little things that I did not get or didn't get done, so we refactored that. So now we'll be able to access storage with a capital S, and we'll access next with a capital N for next. Once it refactors. I may have not done it. Oh, I did it twice. Okay, let's just get rid of this one. Okay, so it looks like we want this to be next, and then next. Fix that up a little bit. Okay, so we have refactored this so that the capital N next is a public property that accesses the private next. That way we can throw some if statements in here if we wanted to for some control. Same with storage. Capital S storage is the gateway or accessor for the lowercase storage. So these are private with accessors. And now when we access, we work with the node class, we're going to have to use these public accessors. And of course the constructor has to be public itself. And that's where that error came from. So let's go ahead and go back to building this. Okay. We have asked for a new node, and basically what we're saying is, operating system, give me the memory for a node and assign the first address of that block of memory of the size of a node, which is in bytes, how many bytes it has. We'll say a node is 10 bytes. And you can actually look up, there's some code that you can write to look at the size of a node, but I'm just arbitrarily saying it's 10 bytes. So let's say it's 10 bytes. That means that it's going to return the first first location, and let's say that that location is 300. And that means that in the RAM at location 300 until 310, that node exists. So that's when it actually assigns that node. And the address that the reference pointer points to, which in this case is head, will point to the node at address 300, and then at that node, since every node that we create, next is automatically starts at null, and storage starts at null. So this is storage, this is next. Next is a reference type. Storage is also a reference type, but we're actually going to be using it to store information. Next is what's going to be storing the next memory location of the next node. Okay, so essentially that's what we've just got done doing, is creating one node that head points to. Its next is null, and its next is null. So what I can do now is I can say head.storage equals 1. And I can also do you know what, let's do something that'll print this information out so that we can, fill the memory up and print the memory. Let's just do a simple list box. So what I'm going to do is I'm going to go and I'm going to add a list box here. And when I run this, it'll create the nodes and add them to the list box. So we'll do list box 1 dot items dot add head dot storage. Okay, so I've asked for the memory, I've filled the storage for the memory, so now I should have 1 in there. Now notice I didn't have to use new there because I'm using a primitive data type. It'll probably work. It shouldn't bug out. Then I am going to print the memory to list box. So I run it, and it's going to pop up here just a second, but we're dealing with 2015, so it could take a while chugging through. Well, looks like it's trying to pop up somewhere. Okay, there it is. We've created the node and we printed it on the list box. So that's kind of what we have right now. So here's what we can do. We can then say, okay, if head is a new node, we can go to heads next. Heads next is here. So we go to head, it points to the next. So I can say here, heads next equals new node. And then I can say heads next storage equals 2. And then of course list box 1. List box 1. Dot items dot add heads next storage. Okay, so what this is doing is we say go to heads next, this reference type right here. And essentially what we're saying is we're saying assign this to another node and make that node or this next point to that node. So let's see what I got here for a diagram. There's another node right here. This is going to be 2. Okay. This next pointer is going to be automatically filled with an address. Let's say that this is at 30. and the operating system said that the address of our new node is 1200. So that means that when we've asked for it, when this line runs, it's going to give us 1200 because that's the access point or the starting byte of the 10 bytes that this node makes up. So essentially what we've done is we've linked one node to another through the next. So this is now the next pointer or reference type. It now points to the next node. And this one, since every time we create a node, starts out with next being null, that points nowhere, and that's essentially the end of our list. So when we say heads next storage equals 2, we're saying go to head, it's next, this guy's storage, and assign it 2. And then we're going to go ahead and add that to list. Now you see this this whole .next behavior. That's the reference type that we're using for the next one, and it can get kind of wacky here, as you'll see in a little bit, because I guess you can probably guess what's going to happen and what we have to do for the third one. Let's go ahead and test this one out. Okay, there's our 1, 2. Okay, so let's do this. Let's say heads next next. Okay, heads next next dot storage equals 3. Okay, and then we're going to do our list box of items dot add heads next next storage. Okay, now let's test this out. So basically what I'm doing is I'm asking for another one of these guys, and I want for 3, and basically let's say that this comes in at address 3000, and this guy is, I want this one to be 3000, and then this one just be 45 or something like that. Simple. And of course the next is null. Okay, so testing it out, running it. Okay, something is not right here because I'm not getting the 3 like we should. And oh, I forgot to ask for it. I forgot to ask for that new node. So we actually didn't create this one yet. So now I have to go here and I have to add that in here. So let's see here. We want the next next. We want to assign that one to a new node. So we'll go to heads next equals new node. Okay, that should actually work. We actually finished and did that appropriately. So now that it's the next, we've asked for the memory, and it gave us address 3000 of the new node. And it should, since we've done all the steps, yep, there we go. 1, 2, 3. All right, so you guys can kind of get the idea here of what's going on. What happens when I add 4? And essentially, it's going to be head.next equals new node. And I think it's going to get old doing .next real quick. So that's why we have what's called a linked list manager. And it's a whole nother object, it's a whole nother class, and what it's designed to do is essentially manage with loops that whole .next behavior. And let's just throw it in here and see if we got it, because I'm going to give you an idea of how those loops work before I quit this video, and basically the next video for linked list that I have will cover that. So, oh, I got to do another .next. Okay, we should be able to test that and get 1, 2, 3, 4. Here's our 1, 2, 3, 4. Okay. How it works with the basically I call it traversing, or basically it's traversing a linked list. And what I'm going to do is I'm going to build a print function, or not a print function, but a print routine. And what it does is it's essentially it's going to be a loop that we can create a node and we can call it the current node, and we can assign it to head. So essentially, we create another one of these guys, and let's see if I can get a no, not that one. Yeah, this one. This one. Let's resize it and let's make this our current. Oh no, horrible. Okay, let me ungroup this one and then we'll use this guy. Okay, so let's get rid of some of these. There we go. Okay, so I'm going to just copy this, paste it, and it's going to be my current. In fact, let me take this guy itself and throw him over here in case we need him again. Okay, this is going to be essentially what we're doing is we're saying give me a node called current. Basically, give me another reference type and let's call it current. Okay, and then what we do is we say current equals head. So we're going to assign it 300 when we say current equals head. Even though it's got its own address, it's totally a different variable with its own address. We're going to say, once we say current is equal to head, because it starts out as nothing, as soon as we say current equals head, we're saying take the value of what's inside of head and store it in current. So essentially, we're telling it to point to the same location. And that I'm going to ungroup here a little bit so that I can take this and copy it and get it so that we got some kind of pointer so you guys can kind of reference that. And basically, current now points to the same thing or the same node as head points to. So essentially, they're the same. So what I can do then is I can say while current does not equal to null, because we're going to be assigning current to each next until it hits that null mark, that means that we're at the end of the list. And while it's not equal to null, let's go ahead and say listbox1.items.add currents storage. And current storage is this number 1 because current is pointing to that first node. So then what I do is I'm going to say current is equal to currents next. And that's the key right there of how to traverse. So what ends up happening is the first time through, current points to the first node. Then we add it to the list box. So the number 1 goes on the list box. Then we say current is equal to currents next. Well, current is going to then hold what currents next has, which is that 1200. So essentially, when this line happens, current is equal to currents next, what we've done is we've taken that and we've said now you are storing 1200, which looks like it's not working. Okay, there we go. That's fine. So now we say point to this guy over here. You're no longer pointing to the first one, you're pointing to the second one. So since current is now holding address 1200, which is the second node, and we say, then the next time through the loop, we say, hey, add current storage. Now current storage is 2. And then the number 2 is added to the list box. And then, of course, we say current is equal to currents next. And then what happens is current is going to be assigned currents next. Since current is pointing here, currents next is holding the address 3000. So now current is going to hold 3000. And it's going to then be pointing over here to this guy. So when that loop runs again, and we say listbox1 items.add current storage, since current is pointing to this link right here, it's going to store and add 3 to the list box. And then what happens is we then say current is equal to current next, which current next is null right there. So then this becomes null. Basically points nowhere, and the loop checks, and as soon as current is equal to null, the loop quits. And head is still maintains the head of the list. And that's why we use another pointer to walk the list, is because essentially if you walk your head, you lose your head. And you don't want to lose your head in a linked list ever. It causes you to essentially lose your links. You always need to maintain that first link, because from that first link, everything is linked from there. If you lose that first link, then you've lost everything. And that's why you don't want to lose your head. Okay, so let's test this out. It should work, and that's kind of how you manage linked lists with a loop. You can then manage using loops and essentially assignment of your pointers or your reference type to make it so that you don't have to do this .next. I mean, imagine if we have, even just 200. That's a lot of .next, to store 200 items on a linked list. So that's why a linked list manager is needed. And essentially, that's what the next video will be on, is how a linked list manager works. And we'll start it with the add front, and I'll continue to use this kind of diagram. In fact, we'll probably use this exact diagram when we come back on another day. All right. Thank you.